Hi, today I'm going to explain the extra credit problem given by our sir. The problem states that this is the PDF of x given as k divided by 1 plus x power 4 and PDF of y given as k divided by 1 plus y power 4. And both x and y are ranging from minus infinity to plus infinity. And our motive is to find the PDF of z, which is given as x divided by y. We know that the cumulative distributive function of z is given as probability of z less than or equal to z. And using this graph, we can arrive at the conclusion that this is the line x equal to zy, and this is the region of y greater than 0, and this is the region of y less than 0. So hence this cumulative distributive function can be split into two probabilities, and this can be expanded using the PDF of the joint distributive function x and y. So using this graph, the limits of this integral varies from y varies from 0 to infinity and x varies from minus infinity to yz, and in this integral the limits of y varies from minus infinity to 0 and x varies from yz to infinity. And we know that the joint density function is given as k squared divided by 1 plus x power 4 into 1 plus y power 4 because both x and y are independent random variables. And in order to find the PDF of z, we are using Leibniz's rule, and hence the differentiation of the cumulative distributive function can be found out as these two integral values. Now these two integral values can be clubbed as 2 times 0 to infinity y into k power 2 and 1 plus y power 4 z power 4 and 1 plus y power 4. This integrand can be written as 1 divided by 1 by z power 4 minus 1 and can be found out using these values. This would arrive at this integral value. And in order to solve this integration, we are using substitution, where we are using t is equal to y square and we are saying s is equal to z square and y square. And on differentiation, we can find out dt and ds. And using these two substitutions, we are finding out the fz of z value, and on integration, we know that dt divided by 1 plus t square is given as tan inverse of t, and 1 plus s square is tan inverse of s. On applying the limits, we have 2k square 1 minus z power 4 and half minus z square divided by 2, the whole thing into pi by 2. And on expansion, we get the PDF of z, which is equal to k square pi divided by 2 into 1 plus z square. Now we need to find k. In order to find k, we're going to integrate fx of x from minus infinity to plus infinity, and we know that this value is equal to 1. So on integrating this from minus infinity to plus infinity, the integral is dx divided by 1 plus x power 4. Now let's see how this is integrated. Now we can write this as 1 divided by x square divided by 1 divided by x square plus x square. And here 1 by x square plus x square can be written in two ways. That is 1 divided by x plus x the whole square minus 2, and 1 divided by x minus x the whole square plus 2. And also the numerator 1 by x square can be written as 1 by x square plus 1, 1 minus 1 by x square and the whole into 1 by 2. And we can split by applying these substitutions in the main integral. We can split this integral into two integrals, I1 and I2. Let's integrate I1 first. I1 is half into minus infinity to plus infinity integral of 1 by x square plus 1 divided by x minus 1 by x the whole square plus 2. And now we are going to substitute this value as t, and on differentiation we get 1 plus 1 by x square dx is equal to dt. So on substituting, we get half into integral of dt divided by t square plus 2. Our motive is to make this t square plus 1 so that we can some variable the whole power 2 plus 1 so that we can use tan inverse formula. So again we are going to substitute t is equal to root 2 tan theta. Now dt is equal to root 2 secant square theta d theta, and on substitution we arrive at this integral, and we know that tan square theta plus 1 is secant square theta, and hence this integral would reduce to root 2 by 4 d theta, which is nothing but theta. And on coming back to the substitution, theta in terms of t becomes tan inverse of t divided by root 2, and this is I1's value, and I2 is minus half into integral minus infinity to plus infinity 1 minus 1 by x square divided by x plus 1 by x the whole square minus 2. And similarly here we are substituting this value as root 2 into t, and on differentiation we have the numerator and root 2 into dt. And again on substituting these into I2, we have this formula, and here after the simplification we have dt divided by t square minus 1, and simply dt can be expanded as this, where we are writing 1 is equal to t plus 1 minus t minus 1 divided by 2, that's nothing but 1. So by substituting this into that integration, we have I2 is equal to minus root 2 divided by 8, and this divided by the denominator, which is t plus 1 into t minus 1, and this value divided by the denominator, which is t plus 1 into t minus 1. On simplification, we arrive at root 2 by 8 dt by t minus 1 and dt by t plus 1. On integrating this, we get ln of t minus 1 and ln of t plus 1, and hence we substitute t values as in terms of x, and this is our I2 value. Now we know that I is equal to I1 plus I2, and hence substituting I1 and I2, we arrive at this. Now on simplification, again we have these values, and later we are applying the limit 0 to infinity, and we get I is equal to pi by root 2. We know that from the first step that k into I equals 1, and now we know I value, and hence we can find out k value to be root 2 by pi. And after substituting this in fz of z, we have 1 by pi 1 plus z square. Now once we integrate fz of z from limits minus infinity to plus infinity, the value turns out to be 1, and hence we know that this is a PDF